Hello everyone. In the last video, we have talked about the basic idea of the cache design. So we would like to map the data in the RAM main memory into the cache limited space. So we have to share the same location for multiple data. In multiple data have to share the same space in the cache memory. So how can we design the cache memory? How can we design the mapping of the cache memory? We need to answer that question in this video. And we'll introduce first type of cache, which is called direct map cache. So for direct mapped cache, then each space, each block, so like the small unit I draw here, each tiny small cell, each tiny location is actually called one block. And then for a direct map cache, then the block size is one word. So this is like the most common the easiest type of example. In future, we may have other cache, like one block in the cache could have multiple words, could store multiple words. So the smallest size of the block in the cache can be one word. So for each item of the data at the lower level memory, and so each item in the RAM, there is exactly one location in the cache where it might go to. Okay, so of course, as we do have many more locations, we do have many more space in the RAM. So in order to map them to only small amount of locations in the cache, then many of them have to share the same location. For example, if we map the same first location to the first block in the cache, and this is the RAM, and we map the second location to the second block in the cache, we can map the third one to the third location, the fourth one to the fourth location. Suppose I only have 4 blocks in the cache. Suppose we only have 4 blocks in the cache. So what will happen? So we map the first 4 into the cache location 1, 2, 3, 4, and then the 5th location will go back to number 1 location again, and the 6th location will go back to number 2 location. The 7th location will map to number 3 block, and the number 8 location will have to map to the last block. So because we do have multiple, many more different locations, in the RAM, so a different location, they will have to share the same block. In a cache. So for this example I draw here, so the number 1 and the number 5 location in the RAM will have to map to the first location in the cache. And the number 2 and the 6 will map to the same location. Number 3 and the 7 will map to the same location. And number 4 and the 8 will map to the same location. So it's pretty easy to understand as we do have limited amount of locations in the blocks in the cache. So multiple data in the RAM will have to share the same location, same block in the cache. So that's exactly same with this figure, right? And then remember, for the memory, the RAM, the main memory. For the main memory. So the first block here in the main memory will be mapped to the first block here in the cache. Right? So is there an index of that? Of course. So we call it address, right? So for each memory block, then the address, we know the address. And what is the address? The address is usually a 32-bit data in MIPS processor. So you could have 0x00000000 if that's a hex address. So you can write it characters here. So you have to have a 32-bit data to indicate the address. But the address could be a word address, could be a byte address. So what do you mean by word address, by byte address? So this is, of course, the first word, and the second location here is considered as the second word. The second location here is, of course, the second word. So it is the second word. It is also the fourth byte. So the starting location of the second row here is the fourth bit. Start with the fourth bit to the eighth. So 4, 5, 6, 7 to the seventh. I guess I should say fifth. So the first block here contains byte 0 to 3. And the second block here contains byte 4 to 7. Byte location 4 to 7. The first row here, we could call it the first word. And so if I call it word 0. And the second row here will be called word 1, right? So maybe I can inside. Let me take the note here. So the first row, the second row, we need to understand what is inside of the first block, the second block in the main memory, and that will be copied to the first block and the second block of the cache. So the first block is containing the byte 0 to 3, and the second block, second unit of the memory contains the data from byte location 4 to 7. And if I do not want to use byte location, well, I can say, well, it is word location number 0. And the second one here is, of course, word location number 1. It's, of course, word location number 1. So what does that mean? That means when you write the address, it could be the real 32-bit binary address. It could be a word address. Okay, so, or sometimes it's even called a block index, because for direct map cache, so one block is only one word. So the blue row here is word 0, block 0, and the pink row here is block number 1, right? So then there's a few questions we need to answer. How to design the direct map cache? Okay, we know we just simply do a mapping. So we put a piece of data into a different location. In each piece of data is put into different location in the cache, and according to the address of the data, then we know where we should put it, right? So remember that we have many data inside of the RAM, and we have limited amount of space in the cache. And according to the location, according to the address, of the data, then we could determine if this is the first data and my cache only have 4 different locations, so I will put it into the first location. And that means the 5th data and the 4n plus 1, 4n plus 1. So the first data, the 5th data, the 9th data, the 13th data. So all of those data, which is 2n, 4n plus 1, 4n plus 1. If I start with 0, then this will be 4n. This will be 4n. So all those data will share the same location inside of the cache, right? So this is like how we determine where should I put the data in the cache, right? So suppose I have the cache and I have the RAM, and the CPU is trying to read a piece of data from the cache inside of the RAM. So you really hope that piece of data is inside of the cache. So you don't need to go all the way down to the RAM to get that piece of data. So it will be much more efficient if the data you want is actually stored in the cache. And we know which piece of data should go where inside of the cache. So we know how to map the data of the memory into the cache. However, do you know if the data is there or not? Do you know if the data is there or not, right? So we know how to determine a particular memory location could be mapped to a particular cache location, but we should also know, is the data inside of the cache or not? That's a big question we need to answer. That's a really hard question, and it's super confusing here. So I hope you could pay enough attention. So there's regarding to if we could find the data in the cache or not, it's not really a simple question. So it's sometimes if this is the first time you use the cache, and then originally we should assume the whole cache, the entire cache is empty. Right? So then, of course, there's no data in it. And later on, maybe some part of the cache is filled by certain data. So some part of the cache is still empty. They're still empty, right? So if there is a piece of data in a certain location, can be represented by one binary bit, and we call it a valid bit. Because we simply need one bit to represent if the current cache location is used or not. Is it empty or not, right? So that's easy to understand. So if we have one binary bit to represent if the current cache block is empty or not, then we could simply save a lot of time. If the cache block is empty, that means you cannot find your data in it, and you have to go all the way down to the RAM. So that's one part. And another question will be, how do I know the data I want is in the cache or not? How do I know the data I want is in the cache or not? So if the data CPU needs is in the cache or not. How do I know if the data our CPU needs, which is needed by the CPU, if the data we need is in the cache or not? Remember, our CPU is trying to check the cache as the first step. And if the data is not in the cache, then you need to go to the RAM, which is far away from the CPU compared with the cache. So we do not want to go to the RAM to read that piece of data. But if that piece of data is not in the cache, then I have to go to RAM to find it, right? So suppose my RAM look like this. So this is my cache. This is my RAM. So the main memory is called RAM. So suppose the RAM look like this, and I would like to read apple So my first memory location stores apple, and my second memory location stores a heart. So according to the mapping principle for direct map memory, direct map cache memory, then the apple should be mapped to the first location of the cache, and the heart should be mapped to the second location of the cache, right? So then, suppose I would like to read the apple, then a question will be, is the apple in the cache or not? How do you know if the apple is in the cache or not? So there is one single bit we just mentioned. So for the cache, it's not simply just one piece of memory keeps a copy of the apple and the heart. It is much more complex than that. So one part is considered to be just the pure data. So how big the data you have here in the memory, then how big the data you have here in the cache. So the yellow part is actually only the data, the pure data. So if you want the apple, then the apple might be here. Suppose the apple is here, then you will be happy because CPU can read it from the cache, and the CPU does not need to go to the RAM to look for the apple. And another thing is, before you consider if the apple is here or not, you should really check the validation bit, because we could put one single bit to represent if the current cache block is empty or not. Suppose it is not empty, then you will have a binary value 1 here. And if it is empty, then we do not need to bother check the data. We do not need to bother check the content because it is empty, right? However, another question, the real question is, how do you know if the apple is there or not? How do you know if the apple is there or not? Remember that the original application looked like this. So the CPU want to read a piece of data, and the CPU doesn't actually know that piece of data, how that piece of data look like. So it actually doesn't know if that is an apple or that is a heart. However, the CPU only knows the address of the data. The CPU only knows the address of the data. So instead of reading an apple, the CPU actually does read the data from address number 0, So the CPU only reads from a certain address, but the CPU does not necessarily know if it is an apple or it is a heart inside of that memory address. However, this memory address is, of course, the RAM address. The RAM address, right? So you have to know the address if you want to read something from the memory. If you want to read something from the memory, then you have to know the address. And how does CPU know if that piece of data originally in that address is in the So how does the CPU know if that piece of data, if the apple is inside of the cache or not? The only thing the CPU knows is the address of the apple. The CPU might not necessarily know if that's an apple or not, but the CPU does know the address of the apple, right? So we actually have to store not only the content, but also the address of each piece of data we put in the cache memory. So unfortunately, we have to do that.